Welcome to video 3 in a part 3 series in which we discuss functors, applicatives, and monads in Haskell. This video will be all about monads. If you haven't watched the other two videos, I highly recommend that you watch them since we'll be drawing from examples from those videos. Just as a refresher to what a functor and an applicative is, we will look at this diagram right over here. And essentially what a functor is that it takes in a function, regular function such as +3 times 2 anything, takes in a wrapped value. In this case, we're just going to use adjust, which is a maybe. And what it does is that it applies the +3 inside the wrapped value and returns us the appropriate wrapped value. So in this case, we would get +5 back. And you can see the code on the right to do that. An applicative takes us one step further. And what it does now is that it takes the function, which we had +3, and it puts it inside a wrapped value. So how it's different from fmap, or how it's different from functor, is that in functor, the function was outside. In applicatives, the function is actually inside, and we still want to apply it to just 2, but we couldn't do it using fmap, so then we had to use an applicative instance, and this is how we did it. If any of this is looking new to you, then I highly recommend you watch videos 1 and 2 of this topic, and it should clear it all up. So now, what is a monad then? So I'm going to start by writing down the definition of monad, and then we're going to see what it is from there. So a monad, just like a functor and an applicative, is a type class. Okay. Now, what does a monad do? So a monad applies a function. So this is a regular function. This is something like, +3 times 2, something like that. Not a wrapped function, a regular function. It applies a regular function to a wrapped value and returns a wrapped value. Okay, now you might be asking yourself, wait a second, is this not exactly what a functor did? Because if we go back to a functor, we have a regular function, +3, we have a wrapped value, just 2, and we return a wrapped value, just 2. So you might be thinking that this is exactly what a functor is, and you're kind of right. Now let me go on and I'll explain what the difference is. Think about how a functor is actually constructed. When we did a functor, what did we do? We did fmap. Then we had f just a to just fa. So if we take a look at what's actually happening here in the instance of a functor, we have a function, we have a wrapped value, and we're getting a wrapped value back. A monad works in a similar yet different manner. Think of this example as a monad. The example I'm going to define is the following. Essentially what it's going to do, it's going to take in a regular number and it's going to check to see if I can divide it by 2. If I can, then it's going to wrap it in whatever the number is, divided by 2. Otherwise, we're going to return nothing. So here's a function I'm thinking of. I'm going to half x is equal to, and essentially what is it equal to? Well, if even x, then we'll return, I'm just going to return adjust x divided by 2. Else, nothing. So now let's actually see how this happens. I'm going to run it right over here. Now if I do something like half 4, we get just 2 back, as expected. But what if I actually want to pass in adjust? What if I want to pass in a wrapped value? How can this work? Can I do something like half just 4? I can't. It doesn't work. So this is where actually the monad comes into play. And the way we actually do it is the following. Have just 4, and then this strange symbol right over here, and then we'll pass into half, and then we'll get just 2 back. So now I'm going to explain what exactly is happening here, and why it didn't work directly, and why it worked when we put in this strange symbol here. So as a recap, what's happening is very similar to a functor. We're still taking in a wrapped value. But the only difference here is that I'm not expecting a wrapped value in any of these parameters right over here. As you can see, this is an x. This isn't a just x. If this was a just x, then I could very easily just do half just 4, and this would give me just 2. But the beauty of a monad is that I don't need to provide a wrapped value in these parameters here. I can just provide a plain value just like this, and what happens is that when I apply this strange looking symbol right over here to my function, then it gives me back what I want. So what's actually happening under the hood? Let's see. So I want you to think of this strange symbol right over here as one of these toilet plungers. And as you can see, it kind of looks like that as well. But what's happening exactly here is the following. So when we do just 4, and then I apply this toilet plunger symbol, what's actually going to be happening is that it's going to be taking this 4, and it's going to be putting it after. So here, we're going to have a 4. So what happens now is that when I did something like just 4 half, what ends up happening is half 4. This half and then this 4 is going to be padded right after it. So that's exactly what's happening when we use this symbol right over here. And we're going to get into how to create this symbol, but I just want to show you one more example before we do that. So let's say I have, so we've already seen this, just 4 goes to half will give me just 2. Now what if I did something like just 3 goes to half? Well, as you can see, 3 does not evenly divide 2. So this is actually going to be false. And so we should get back nothing. So we get nothing back. What if I do nothing to half? Well, you can think of this analogy again. If this is taking whatever's in here and putting it after, if there's nothing there, it's just putting nothing after. So then we should get nothing, just like this. Now, a cool thing you can actually do is chain these together. So what will happen now is if I do just 4 half, then what if I did half again? We get just 1. What's happening here? This is returning just 2. Again, just 2. The strange symbol and then half. The 2 goes after the half. So this is the same as just saying half of 2, which is 1. And that's exactly what we get right over here. As you can see, if we do this one more time, then we should expect to get nothing, because 1 does not evenly divide 2. So now let's get to actually how do we create our own monads. Alright, now let's actually see how we can write it out using the formal definition. So a monad, just like a functor and applicative, is a type class. So that essentially means that it's going to give us a method to define, and we're going to define it. So we have class monad m, where, and the method it defines or gives us a signature for is this strange symbol right over here. And this symbol is actually known as bind. So this is called a bind symbol. You could call it toilet plumber, whatever you want. So it takes in MA, and I'll explain what these mean in just a second. A to MB, MB. Okay. So now what is this M? M is essentially your monad. Okay. So when we say MA, what is MA? MA refers to, in our example, it refers to the just to 4. Okay. So just to 4 is a monad. More precisely, maybe is a monad. Just to is just an instance of maybe, but again, it follows the same logic. Just to 4 is the monad. Okay, so then what is this right over here? Well, this is a function. So A to MB is a function, and it takes in just a simple value right over here, and it returns to us a monad. And can you guess what that is? Exactly, this is the half function. What does half do? Half takes in a simple value, and it returns to us a monad. Just 2. Nothing 2. Monad. Finally, this is what the bind will return. It'll return a monad. So let's see this in action when we actually do the implementation of monad for maybe. So let's do that right now. So just as we defined it in the other videos, we'll define it the same way. So we will have instance, monad, maybe, where. And again, monad, we have 2 cases we need to handle. We need to handle, and this should be maybe 2, to and do nothing. And remember how we can write it just like this. You can write it this beginning and then this and the next parameter, but this is how it's actually going to be used, so it makes more sense to write it this way. So nothing to a function. So MA, this is our MA, and here's our function, which is this. We're going to have the same thing for just2, so just2 value with some sort of function. Well, what is this equal to? Well, very simply, if nothing is going in, then there's nothing here for me to actually apply to the function, so nothing goes out. In the case here, I actually have something, and so I'm going to apply it to this, and this is it. Now you may be thinking to yourself, why am I not surrounding this with a just? Like here, this is clearly a maybe object, but this is it just seems like I'm applying a function to a value. Where's actually the just happening here? And the beauty of a monad is that, look what it's returning. It's actually returning a monad. So what it's going to do is going to automatically put this inside a just2 for us. How's that happening? Well, you see right over here, this function takes in a simple value, val, and it returns to us a monad. So this function right over here, which is our half, when we do something like half val, it's actually going to return to us just2 with whatever value it needs to do it with. So that's why we don't need to put the just2 around it. So now I'm actually going to change this to be just2 and nothing 2. So now let's see this in action. Let's actually recompile it and see what happens. We're getting an error. Now what is this error saying? No instance of applicative may be 2. The thing about monad is that you can't define it alone. If you remember from our applicatives, applicatives use functors. And functors were able to survive on their own. But now monads needs to use both applicative and functors. So what I'm going to do is I'm going to paste in, and you can get these from the last 2 videos. I'm going to paste in the functor definition and the applicative definition. Now if I recompile it, it should work, no problem. And now let's do with the half method. So what we did, we had something like just2, let's do 8, half, we get just2 4 back. And you're going to see something. If I remove this, I do this, well, it's not going to know what this strange symbol means. And this is exactly what's happening. Now, if a data type has a functor, applicative, and monad, we essentially say that it has all 3. So maybe is a functor, maybe is also an applicative, and maybe is also a monad. So this is essentially how a monad works. We take in a simple value. So in the example here, the simple value is something like 8. We apply it to the function, and we get back, well, I have to recompile it, and we get back just 4. So now I'm going to take this one more step of the way and do it on a personal example. Alright, so here is our example. In the last 2 videos, essentially what we had was, we had a tree, and it was defined by a tip and a branch. And essentially this is what it looked like. So we would have something like this. So these 4, 5, 6 are the tips, 4, 5, 6, and the branch is each of the arrows that are pointing downwards. So what we could do is the following. We had x is equal to the following, and then I just do x, and it gave me that. Now I'm going to define a monad instance for this data type. We've already saw previously that in order for us to define monad, we already need to define applicative and functors. So I did that in the first 2 videos, so I'm just going to paste that in right over here. Now finally, let's go and start doing the monad. Alright, so let's define how we're actually going to be using it before we actually define the monad itself. So when we did the just2, we had just2, something like 4, and then we had half. Now the way we're going to do it for the tree, so x is the tree, so we're going to be passing in something like x and then some function right over here. Now this function I'm going to define right now. So what is this function going to be looking like? Let's make it something very, very simple. So let's just do something like, so I have a lot of f's here, so I'm just going to choose g instead. So let's just do gx, and I'm going to see if x is equal to 4, then I want to return tip Let's do 99. Otherwise, what I want to return is, let's just do branch, and then we'll do tip x times 2, and then let's do tip x times 4. And this is all inside a branch. Okay, so now let's refresh this. Now if I did something like G4, for example, what am I getting? I'm getting tip 99 as expected. If I did G12, I'm getting tip 24 and 48, which makes sense. So what's actually going to be happening is when I do something like this, when I do x with this function right over here, which is g, what I want to happen is the following. So this x that we have, when I do x to g, if this x is a tip, then this 4 right over here is going to go in the place of x. The 5 will go in the place of x. The 6 will go in the place of x. So what you should see is this is basically allowing me to create more trees. So 4 is going to be replaced by another tip 99. This tip 5 is going to be replaced by a branch containing 10 and 20. Tip 6 is going to be replaced by a branch containing 12 and 24. So let's now do that for the monad. So we've already done applicative and functor. So now let's just do the monad. And now how are we going to do the monad? So let's have instance monad tree where what? Well, we need to handle two cases, the tip and the branch, and we need to make sure we're doing the bind operator. So let's start with the tip. So if you have tip A, we have this bind operator to the function, let's just call it f. What do we want to happen? Well, think of the plumber. We want this to go after. So it'll be f A if we have a branch. And branch we have left and we have right. And we have this going to the function here. Well, obviously we can't just apply it directly. We need to recurse to our base case. So we will do branch. We will do left with the function. And we will do right with the function. As you can see, it's very natural. Just recurse down to the base case, and then here's our output. So now let's actually see this in action. Again, here we have x. If I do x to g, now to make sure you really understand this, what's actually going to happen is this tip 4 right over here will become a tip 99, and this tip 5, where you can see that it will fall under this branch category. So it should become 10 and 20. So let's do that again, and we made right here. So became a tip 99. Now this thing right over here, the tip 5, became a tip 10 and tip 20, and the other one became a tip 12 and tip 24. So again, what was happening is that when I did something like tip 4 to G, this 4 goes after G. And so this is why I got tip 99. If I did something like tip 3, tip 5 to G, then it's going to recurse down to its tip, and then it's going to apply this G function on top of it. So this is how we did functors, applicatives, and monads in Haskell. Now there's many things in Haskell that basically have all of these defined for them. Maybe being an example, either being an example, this tree I just defined being an example. A lot of things have functors, applicatives, and monads defined for them in Haskell. I hope that these 3 videos have been helpful for you, and good luck with your studies of Haskell. Thank you very much.